Okay, so again, we discuss what are the names and label that we give to the part of the ray diagram, because all of these names are very important. It will help us describe, help us in our discussion of how an image is formed by using a ray diagram. Okay. Alright, so we want to continue. Okay, here we want to learn how to find out the focal length for a convex lens. Okay, previously we learned that focal length. Okay, focal length is the distance between focal point and optical center of the lens. So focal point is the distance between focal length is the distance between focal point and optical center, which is here. So focal point is the point located at principal axis of a lens where parallel light ray will converge. That means all the light will converge on this point. So this point is a focal point. So the distance from focal point to the optical center is the focal length. This is very important because a lot of students make a mistake of measuring the focal length from the focal point to this surface, to here. Okay, which is wrong lah. Okay, the distance, the focal length is distance from focal point to optical center, not to the surface of the curvature. Alright. Okay, so if you want to find out the focal length for convex lens, all we need to do is just do a very simple experiment. Okay, we just take convex lens. Okay, we put and then we put somewhere where there is a bright light. Okay, got bright light coming in. For example, here is window of laboratory, and then on the other side we put a white screen. So the light that pass through the convex lens, it will converge. Okay, it will converge onto the screen and an image will be formed. So like this. Okay, for example, this is the object. Okay, this is the object. You look at this condo outside here, and then there's a wall here, got flower pot. Okay, so after the light from outside pass through the convex lens, okay, pass through convex lens and land on the screen. Okay, on the screen here. So this piece of white paper, this is the screen. So you can see that an image will be formed on the screen. Okay, you can see that it's upside down. This is the roof here. This one, this is this, and then you see the wall. Okay, you can see the wall. Okay, here the wall. Okay, you see this the signboard on the door, signboard on the door of the lab. Okay, like this. So you can see that there is an image that is formed on this piece of paper. This piece of paper is the screen. Okay, this piece of paper acts as the screen. Okay. So this type of image is what we call a real image. Okay, a real image, because light converge on the paper and form an image that you can actually see on the paper. So we call this a real image, because really got light fall on the paper. Okay. Okay, so the light come in from outside, pass through the convex lens and converge on the screen. Okay, on the screen and form a real image. Okay, form a real image. Okay, now to find out the focal length Okay, so this is the reading of the screen. Okay, position of lens is at 1 centimeter. Okay, it's put at 1 centimeter. And the position of screen, as we can see here, is approximately 12 centimeter lah. Okay, so okay, we take it as 12 centimeter lah to make it easy. Okay, to make it easy, we take it as 12 centimeter. So the position of screen is 12 centimeter. Okay, we take the center lah. Take the center. Okay, 12 centimeter. So the focal length will be 12 minus 1 equal to 11 centimeter. So the focal length of this convex lens is 11 centimeter. Okay, 11 centimeter. This position of lens means okay, we put the ruler here. Okay, we put the ruler from the screen to the lens holder or to the lens. Okay, this is a ruler. So this position of lens, this 1 centimeter means that we put the lens here at 1 centimeter. Why we want to put at 1 centimeter? Why do we don't want to start at 0? This is to avoid n error or to avoid 0 error. Okay, so we start at 1 centimeter because the meter rule usually there will be n error. That means the due to wear and tear. Okay, due to wear and tear, that means after use the meter rule for very long time, the 0 of the meter rule is not clearly seen. Okay, you cannot see the 0, the starting of the meter rule clearly. So so that is what we call n error. Okay, n error, if you still remember lah. Okay, n error. Okay, so we start at 0. We put the lens at 0, and then the distance between the lens and the screen, this will be the focal length. Why the distance between the lens and the screen is the focal length? Because the light that come in from outside is parallel. Light that come in from outside is parallel, and all of the light converge to one point on the screen. Same like this. Okay, light come in parallel, focus on one point, converge on one point. So that point is the focal point. That means this screen here will be the focal point. Okay, the focal point will be the screen. Okay, focal point is the screen, and the distance between the screen and the lens will be the focal length. Okay, will be the focal length. So of course, when we set up this apparatus, we need to adjust the position of the widescreen. Okay, you see number 3 here. Place the widescreen behind the lens and adjust its position closer or further from the lens until a sharp image is formed on the screen. That means you adjust, you move this forward or backward. Okay, whichever that is you feel that will get a sharp image. Okay, you adjust until you can get a sharp, a clear image on the screen. So for example like this okay, like this is considered as quite good okay, a sharp image. Okay, and then after that we measure if the image becomes sharp, the image becomes clear already, then that means the screen is at the position or is at the point where the light converge. Okay, it's at the point where the light can converge. Then the image will become sharp. Okay. Okay, so that is how we get the focal length of a convex lens. For concave lens, we cannot do any activity to determine the focal point, because the concave lens cannot form a real image. Okay, because the light is diverged. Okay, the light spread out by concave lens, so the light cannot concentrate on one point, so you cannot get a real image. Okay, you cannot get real image, so you cannot determine where is the focal point. So you cannot find out where is the focal point. You cannot measure the distance between the focal point and the lens, so we cannot get focal length for concave lens. Okay. Okay, so let's look at the discussion here. Okay, light ray from source which are far away will appear to be parallel. Okay, this is very important. Why is it that we say light that come in from outside the window is parallel? Okay, why we say the light that come in from outside is parallel? Remember, in order to get this, to get the focal point, the light that come in must be parallel and then concentrate on one point. Okay, the light that come in parallel, concentrate on one point, so the distance between that point and the optical center is the focal length. So that means first we need to get the light that is parallel coming in. So how to get the light that is coming in parallel? Okay, make sure the light come from far away object. Okay, light from far away. And light from far away is parallel. Why light from far away is parallel? You see, okay, let's say that let's say I draw two lines. Okay, one light source is here. Okay, one light source here, another light source here. Okay. No. Okay, let's say that one light source. Okay, let's say this is the screen. Okay, this is the position where you view the light. Okay, this is the position where you look at the light. So one light come from this point, another is come from this point, which is near. One point is near to the one light come from the point that is near to you, another light come from a point or come from a source that is far away from you. Okay, so the light that is near to you, okay, will be like this. And then this one light come from far away. Okay. Okay, so you just look at this. These two lines, line AB and line CD, do they look parallel or not? AB parallel or not? Look not parallel, right? Okay, not parallel. CD, does it look parallel? Also not parallel. Okay, but for this CD, where the light comes from very far away, if you look closely, okay, it's like this. This AB definitely not parallel, but this CD look like a bit parallel, right? Okay, but and then you zoom in some more, it looks like a bit parallel, right? A bit parallel. And last some more, okay, you will see that it looks like parallel. Okay, a bit like parallel, okay, a bit like parallel. The reason is because this one, the distance is not far enough lah. But if the distance is very far, the further away it is, the more that it will look like the two lines will be parallel. You understand what I'm saying? Okay, let's say okay, this one you feel like not parallel. Okay, now what if I make it longer? Okay, like this look like not parallel. Again, when you zoom in, it look like parallel. Okay, this line and this line, okay, look like parallel. You understand what I'm saying? Okay, look like parallel. The further away the light source, the further away the light source, the light that comes that reach us, it will look like parallel. Okay, the further away it is, the more parallel it will be. Okay, get the idea? Okay, so light that come from very far away places, it will be parallel. Okay, light that come from far away place. Okay, this one looks parallel. This one definitely not parallel lah. So the light that come from very near source is definitely not parallel. But light that come from far away source, it will look parallel. Okay? So that means the light that comes from outside the window is considered as from object that is very far away. So that means when the light reaches the lens, the light will be parallel. And then the light that is parallel pass through the convex lens, it will converge at one point. And that point we call it the focal point. So the distance between the focal point and the lens is the focal length. Alright? And that is how we get the focal length. Okay, so number 2, parallel light ray passing through a convex lens will converge at focal point. A screen placed at focal point will allow a real image to form on the screen. This activity cannot be used to estimate focal length of concave lens. Okay, cannot for concave lens because it is unable to form real image. Okay, so for concave lens, we cannot do the same thing because concave lens cannot form real image. Alright? Okay, okay, next. Position and characteristic of image formed by lens. Okay, we want to find out where is the position of the image and what will be the characteristic of image that is formed by lens. Okay, so the experiment that we do is to determine the position and characteristic of image formed by convex lens and concave lens for different object distance. Okay, so the apparatus we use a convex lens with a focal length of 10 cm, concave lens of focal length 10 cm, ray box with with transparent paper marked with an arrow as object, power supply, lens holder, white screen, and meter rule. Alright, so first for convex lens. Set up the apparatus as shown in the figure. So we have lens holder, convex lens at the center. One side is we have transparent paper with arrow. So this is the object. This is the object. This arrow is the object. And then on the other side there is a white screen. Okay. So the distance between the lens and the arrow, okay, distance between the lens and the arrow will be the object distance. And the distance between the lens and the screen where the image is formed will be the image distance. Okay? Alright. So place the convex lens so that its object distance is 30 cm. That is, the object distance is more than 2f. That means the object distance is more than double the focal length. This lens that we use have the focal length of 10 cm. So 2f will be 20 cm. So more than 2f, 30 cm lah. Okay, 30 cm. Anywhere that is more than 20 cm is the object distance more than 2f. Okay, so we put the object far away, 30 cm away from the lens. Adjust the position of the screen until a sharp image of the arrow is formed on the screen. Observe the image formed on the screen and record its characteristic in a table. Okay? So when we talk about characteristic of image, okay, when we say characteristic of image, what we mean is first, the magnification. The magnification of the image. That means is the image bigger or smaller or same size as the object. Second is the orientation. Orientation, that means is the image upright, inverted, or laterally inverted. Upright, that means okay. Upright, that means like this lah. Upright. Inverted, that means terbalik. Laterally inverted, that means left right, opposite to each other, left right. Okay. So for example, if the object is like this, laterally inverted means it become like this. The image become like this, so it's laterally inverted. Okay, get the idea. So if this is the object, image become like this. So this is called laterally inverted. Okay, this is upright, this is inverted. Okay, so orientation, and then the third one is the type of image. Type of image, so that means is the image real or virtual. Okay, if real image, that means the image can form on the screen. Okay, the image can form on the screen like this. Okay, image can form on the screen. So this is real image. Virtual image, on the other hand, virtual image is you can see the image with your eye. Okay, if virtual image, virtual image is, for example, okay, concave lens. You can see the image. Okay, you can see image with your eye. You can see, but there is actually no light here. Okay, over here there is no light. Okay, if you put a screen here, there's nothing will form on the screen. Okay, so this is what we call virtual image. An example of virtual image is when you look in a mirror. When you look in a mirror, you can see an image, right? Okay, you can see your face. Okay, you can see your face. This is the image. This is object. You can see your image. If you can see image, that means the light, there should be light going into your eyes, but is there any light behind the mirror or not? No light here. No light source at the back of the mirror. Of course, because the mirror is opaque. The mirror is not transparent. Okay, the mirror is opaque, you cannot see through the mirror. So actually there is no light at the back of the mirror, but you can see like there is something at the back of the mirror. You can see that the image is at the back of the mirror. Okay, you can see like got object, got thing behind the mirror. So but there is actually no light behind the mirror. So this is what we call virtual image. Okay, you can see the image, but there is actually no light over at the position of the image. There is actually no light over there. So this is a virtual image. Real image actually got light. Actually really got light. Concentrate, shoot on the shine on the screen and form the image. That is a real image. Okay. Okay, so type of image, and then the last one is the position. Position basically means where is the image? Is the image same side as the object, or in the opposite side of the lens as the object? How far is it away from the lens? That means the image distance. Okay, that means the image distance. So when we want the position, that is what we mean. We want the image distance. Okay, so when we talk about characteristic of image, what we mean is magnification, orientation, type of image, and position of the image. Okay, that is what it means by characteristic of image. Okay, Okay, so choose a suitable scale and draw the ray diagram for convex lens of focal length 10 cm and object distance 30 cm on a piece of graph paper. Determine the position of image and record in the table. Repeat step 2 to 5 for object distance 20 cm, 15 cm, 8 cm. So this 20 cm is the object distance equal to 2f. Okay, this 15 centimeter is the object distance is less than 2f but more than f. That means in between f and 2f. 8 centimeter, that means the object distance is less than focal length. Okay, less than f. Okay. Okay, so this is the table where we write down the result. Okay, so object position. Okay, further from lens, that means more than 2f, is we put 30 centimeter. Okay, we put 30.0 because we measure using meter rule, and meter rule we can measure until 0.1, so we put 30.0. Okay, at 2f is 20.0 centimeter. Between f and 2f is 15. Between f and optical center is 8.0 centimeter lah. Okay, according to this experiment lah. Okay. Alright, so this is the image distance, this is the image position, characteristic of image. This is real or virtual, upright, inverted, the size of image. Okay, so you can see this is the 4 thing lah. Okay, the characteristic of image here. Okay, this 4 thing. Image position, real or virtual, that means type of image. Upright, inverted, that means the orientation of the image. And then the size of image, that means the magnification of the image. Okay, bigger than object, same as object, or smaller than object. Okay, so this is for concave lens. Okay, now we want to because we are unable to do the experiment. Okay, you only do this in your school lah. Anyway, what is important here that we need to learn is we need to learn how to draw the ray diagram, and from the ray diagram we can find out the characteristic of the image also. Okay, that means we don't need to do the experiment. Also, we can find out the characteristic of the image. Okay, okay. Now we want to learn how to draw ray diagram. Okay, ray diagram can be used to determine the position and characteristic of image formed by convex and concave lens. Okay, so rays used in the drawing of a ray diagram. For convex lens and concave lens, there's a little bit different lah. Okay, basically what we are discussing here, what we are going to discuss here is the rules in drawing the ray diagram. Okay, so first we look at the rules for convex lens. Okay, number 1, ray which pass through the optical center travel in a straight line through the optical center without being refracted. Okay, that means if we draw a line pass through the optical center, then the line that we draw is straight through. Okay, pass straight through. Okay, not going to refract, not going to bend. Second, a ray which is parallel to the principal axis is refracted and passes through the focal point. Okay, light that parallel come in, it will pass through the focal point. So this is the same as what we see before lah, right or not? You see here, if the light come in parallel with the principal axis, then it will converge to the focal point. So this is actually the same thing lah. Okay, not something new, not something new. Light that come in parallel pass through the focal. Actually, this one, the first one, light that pass through the optical center will not be refracted, it will pass straight through, is also something that we already mentioned before. Okay, if you look at here, the optical center, okay, point at the center of lens, light ray pass through optical center are not refracted. Okay, light ray passing through optical center are not refracted. Now you see here. So that means this is also something that we already discussed before already. Okay, the first one, light pass through optical center, not going to bend, not going to be refracted. Second, light that is parallel go into the lens. Okay, it will converge to the focal point. And then the last one, the third one, the light ray that pass through focal point will be refracted parallel to the principal axis. Okay, so you see light parallel come in, pass through focal point. Light pass through focal point, parallel go out. Basically just the opposite. Okay, this is number 3 is the opposite of number 2 lah. Okay, so this is the rules for convex lens. Okay, later only we discuss the concave lens. Okay, we concentrate on convex lens first. Okay, so look at the page where we have the result. Okay, the place where you can draw the ray diagram. Okay, so the result first for convex lens. Okay, object distance 30 centimeter. Okay, so this part is very important. Make sure that you practice to draw. Okay, practice to draw. Okay, first we need to position our lens lah. Okay, position our lens. So we put the lens here at the center. Okay, we draw one line. We don't actually draw the lens, the convex lens. We only draw one line because this line will represent the center of the lens or the axis of the lens. Okay, the axis of the lens. So we draw like this to show that this is a convex lens, and we also label okay, we label that this is a convex lens. Okay, and then after that we label the focal point. Okay, so this is the focal length here is 10 centimeter. Okay, so we put here lah. Okay, this is 10 centimeter. Okay, here to here, this is 10 centimeter. Every one unit, one small box here represent 1 centimeter lah. So this is we label as F for focal point. And then here it will be 2F. Okay, that means double the focal length. And because the lens have two sides, because the lens is transparent, right? So that means they will have the focal point and the double of the focal length, okay, on both sides. Okay, this one is F, this one is also 2F. So you see both sides also the focal length is the same. This one focal length 10 centimeter, this one also focal length 10 centimeter. Okay, because the lens, okay, the lens that we discuss here is all where the curvature on both sides is the same. That means the most basic type of lens. Okay, we don't learn about all the other type of lens. Okay, all the complex one we are not going to discuss. Okay, we only we want to learn the basic concept, so we only discuss the most basic lengths. Okay, so that means the curvature on both sides is the same. So the focal length on both sides will be the same. Okay, so the first one, the object distance is 30 centimeter. So we draw the object here. Okay, so this is the object. We draw a triangle here to show that this is the head, this is the tail. Okay, this is the head, this is the tail. Okay, now we want to draw the light ray. Okay, we want to draw the light ray. I use green color lah. Okay, green color. Or I use yellow lah. Okay, yellow to show the light ray. Okay, so we want to draw the light ray coming from the object and pass through the convex lens. What we use the 3 rules. Okay, the 3 rules just now. Okay, so we can use number 1, number 2, or number 3 also can for this case. Okay, so for example, the first one I want to draw is the light pass through the optical center. Okay, for example, okay, I want to draw the light pass through optical center. So from the head, pass through the optical center. Okay, it will go straight through, not going to be refracted. Okay, it's not going to be refracted, so it will just pass straight through. Alright, so like this, pass straight through, and we draw arrow to show the direction of the light before the lens and after the lens. Okay, before the lens and after the lens. And then for the second one, I use number 2 lah. So light parallel come into the lens and pass through the focal point. Okay, light that pass through the light that come in parallel, it will pass through the focal point. And again, we draw arrow before the lens, after the lens. Okay, so we see just by using these 2 lines, these 2 light rays, we can already find the position of the image. Where is the image? You see the light pass through, go to here. This one pass through the lens, go to here. So you see this is the point of intersection. Okay, point of intersection or point of convergence. Okay, point of convergence or point of intersection of light. So that means the light converge here, the light concentrate here. Okay, that means if the object distance is 30 centimeter, the light from the object will concentrate here. It will focus here. So if focus here, that means an image will be formed here lah. Okay, there will be an image here. So I use blue to draw the image. Okay, and then you see this is the tail and this is the head. Triangle over here. Why I draw triangle over here? Because this light come from where? This light come from the head. Okay, the light come from the head, so of course you can see the head is over here lah. And then why the tail is over here? Because you see this tail is over here, so the light that come from the tail pass through the lens and it will concentrate here. Okay, so that means you will see the tail here, the head over here. So that means the image will be inverted. Okay, the image is inverted. Okay, okay, continue. Alright. So you need to learn how to draw this ray diagram. It's very important because in SPM the question can come out where they ask you to draw the ray diagram. Okay, question can come out, ask you to draw ray diagram. So make sure that you know how to draw the ray diagram. Alright, so let's label. Okay, we label the object as O. We label the image as I. Okay, we got capital O, capital I. Okay, so from here we can determine the characteristic of the image. So the first one, we like what we discussed just now, there are the four characteristics of image. The first one is we want to see whether it's magnified or diminished in size. Okay, magnification. That means we want to see whether it's bigger than object or smaller than object. So this one is obviously smaller than the object. So we say that the first one, the magnification is the image is diminished in size, or we can also say smaller than object also can. Diminish in size, that means the size become less. Okay, diminish in size. Okay, after that we want to look at the orientation. Is it upright or inverted? So this is inverted. And then we want to see whether this is real image or virtual image. So this is real image. Why real image? Because really got light focus on this point. That means you put a screen here. Okay, you put a screen on this position and the image will form on the screen. You can see the image on the screen. Okay, so this is real image. And then the last one is the position. Okay, the position of the image. That means we want to know where is the position, and when we say position, that means the location and also the image distance. Okay, so the location is or we give the image distance first. Okay, so image distance is, so here to here this is 10. So here is 15. So 15 centimeter. Okay, 15 centimeter, and the position is between F and 2F. Okay, like that. Okay, so done the first ray diagram. So out of the three, we only need two to get the characteristic of image. Okay, out of the three ruler, we only need to use two to get the ray diagram, to get the characteristic of image. But if you want to draw all three, also can. But some position, some object distance can draw all three, some cannot. Okay, some can, some cannot. So for example, this one, the first one, you can draw all three. So for example, the third one, okay, let's say I draw the third one. Okay, the third one is the light pass through the focal. Okay, light pass through focal and pass through focal point, and then the light will come out parallel to the principal axis. So you see all of them converge at the same point. Okay, that form the image. All of the light, okay, don't care whether pass through optical center or parallel or pass through focal point, it will all converge here. So this is where the image is formed. Okay, all right. So Okay, let's record the result, okay, in the table. Okay, so the object distance is 15. Oops. Okay, 15.0 centimeter. The image position is less than 2f more than f. Okay. So characteristic of image is real, inverted. Size of image is smaller than object, or you can measure the size using ruler also. Okay, can measure the size using ruler. So here we will just say that it's smaller. Just say that it's smaller lah. Okay, smaller than object. Smaller than object. Okay. Alright. So next is object distance at 20 centimeters. So same thing. First we need to draw the length. Okay, here and here. Here and here. F to F. F to F. So this is convex lens. Okay, now the object is at 20 centimeter here. Okay, so when we want to draw, so same thing, the three rules. Number one, we pass through the optical center. One arrow before, another arrow after. Okay, after the lens. Okay, number two, parallel in, and it will pass through focal. One arrow before, one arrow after. So you can see that the light focus here. Okay, the light focus here. So just now I used blue color. Okay, so that means the image will be here. Okay, so this is object, this is image. So from here we can see what are the characteristics of the image. Okay, so first the size. So we can see that it's the same size. Okay, same size as object. Second is inverted. The third is real image. The fourth is the position. So the image distance is 20.0 centimeter. So the position is at 2f. Okay? Okay, at 2f. Okay, here 2f. So fill in the table. So the image distance 20.0 centimeter. Image position equal to f. Okay, real inverted, same as object. Okay, next. Okay, so the object, okay, object distance is 15 centimeters. So same thing, position of the lens, okay, position of the lens, convex lens, this is F2F, F2F, okay. So the position of the object, 15 centimeters, so here. Okay, now draw the light ray. First, pass through the optical center. Okay, one arrow before, one arrow after, and then the second one straight parallel in and pass through the focal. Okay, one arrow before, one arrow after. So the light focus here. So this is the position of the image. Okay. Now the characteristic. Oh, label first. Okay, this is object. This is image. Okay, so characteristic. Here got more space. So it is magnified. That means bigger than the object. Second is this is inverted real image. And the position is V equal 30 centimeter, 30.0 centimeter, beyond 2F or more than 2F lah, also can. Okay, beyond 2F. Okay. Alright, so let's fill in the table. So this is 30.0 centimeter. Image position more than 2F. Real. Inverted. Larger than object. And then you want to draw the object distance is 8 centimeter. Okay, it is 8 centimeter. Okay, so this is the length. Oops. Black carbon. Okay, this is the lens. Okay, this is convex lens. F2F. F2F. Okay. Now the position of the object 8 centimeter, so over here. Okay, now light ray. Okay, so the first one, pass through optical center. Alright, so one arrow before, one arrow after. Another one, parallel in, pass through focal. In, pass through focal. Okay? Alright, so you see, now the light does not converge, it doesn't focus on one point. Okay, the light does not focus on one point. So where is the image? Okay, the light come out. If your eye is here, you look at the light that come from the lens. Okay, look at the light that pass through the lens and go into your eyes. What is it that you can see is that the light looks like coming from here. Okay, looks like the light come from okay, the light looks like come from here, you see? Looks like the light go in this direction, the actual light go in this direction, but it looks like the light, from your point of view, it looks like the light come from this point here. Okay, so because here there is actually no light, there is no light here, so we draw dotted line. Okay, dotted line. And we can see that the light looks like come from here, come from this point. So the image will be here lah. Okay, looks like the light come from here. Okay, so the image is here. So this is the image, this is the object. Okay, like that. Looks like the light come from here. So you will see that the image is over there. Alright. So now the characteristic of the image. Okay, so the first one is magnify. Okay, it's larger than the object. Second, it's upright. Okay, upright. So the head is on top, not at the bottom. Okay, so it's upright. So this is real or virtual image? Here, no light actually. There's no light here. So that means if you take a screen and you put here, there's nothing on the screen. Compared to all the other, this one, if you put a screen here, you can see the image here. Okay, if you put a screen here, you can see the image. If you put a screen here, you can see the image. But this one, you put a screen here, there's nothing on the screen because there is actually no light. It just looks like the light come from this point. Nampak macam, looks like nampak macam the light come from here. Okay, but actually there's no light lah. Okay, so that means this is not real image. That means this is virtual image. Okay. And the position of the image is beyond, so this is 1, 2, 3, 4, 40 centimeter. Okay, so the 40.0 centimeter, and it is beyond 2f. Okay, that means more than 2f lah. Okay, beyond 2f, same side as object. Okay, this one same side as object. Want to write also can, don't want to write also can lah. I mean, not so important, but this is extra detail lah. Okay, extra detail. So beyond 2f, same side as object because on the same side as the object from the lens. You see, both at the same side. The rest, this one is all on the opposite side. You see, on the opposite side of the lens, on the opposite side of the lens, opposite side. This one, it will be on the same side of the lens. Okay? Alright, so let's fill in the table. So this is 40.0 centimeter. This is more than 2f. Is virtual, upright, larger than object. Okay. Okay, now this one we want, this is like something extra. So to look at two special cases. Okay, these two ray diagram will look at two special cases. What will happen if the object is at infinity? That means the object is at the position that is very far away from the lens. Okay, what happened to what will be the image? Where will be the image if the object is at some place that is far away from the lens? So if the object is far away from the lens, so that means the light that come in, it will be parallel. Okay, light that coming will be parallel. So we see how to draw the ray diagram if the object is at infinity. Okay, convex lens. F2, F2. Okay, now object and infinity, so we say that the object is so far away that we cannot see lah, we cannot put inside this ray diagram because the object is very far away. Okay, so if the object is very far away, so the light that come in, it will be parallel. Okay, the light that come in will be parallel, and if the object is very far away and we can still see the object, it will means that the object must be very big. Okay, the object will be big. So if the object is big, so that means the head, the light that comes from the head should come from the top. Okay, come from the top. So we draw like this. Okay, we draw that the light coming in, number one, pass through the focal, pass through the optical center is at this angle. Okay, the light come in like that, and then okay, the second ray, it is parallel to the first ray. Okay, parallel to the first ray, because like what we discussed previously just now, we say that if the source of the light is from very far away, then when the light come here, it will look like the lights are parallel. Okay, it looks like they are parallel. So for this one, we cannot use the rule number 2, because rule number 2, the light must be parallel to the principal axis. But this one, the light must be parallel to the first ray. Okay, all of the ray must be parallel to each other. So that means we need to use number 3. Number 2 cannot use, we must use number 3. So the light that come in, they pass through the focal and come out, it will be parallel out. Okay, it will come out parallel in, out like this. Okay, so what happened is, you see the point of convergence or the point of intersection of the light, it will be at the focal point. Okay, it will be at the focal point. So the image is at the focal point. So this one, the object at infinity, this is the image. Okay. So characteristic of the image. So first is diminish in size, inverted real image, and the image distance will be 10.0 centimeter at F. Okay, at the focal point. So if the object is very far away, then the light that comes in, it will focus at the focus at the focal point. So the image will form at the focal point. So this is actually the ray diagram to show this. To show what is happening here. Okay, light coming from very far away places. Okay, and it will focus at the focal point. So this is to show this. Okay, so the ray diagram show this what happened here. Alright. Okay, next we want to look at if the object is at the focal point. Okay, what will happen if the object is at focal point? You see, object infinity, the image at focal point. Now what will happen if the object is at the focal point? Convex lens. Okay, so the object at focal point. So the object is here. And first ray pass through. Okay, number one, pass through the optical center. One before, one after. And then the second one, parallel and pass through focal. One arrow before, one arrow after. Okay, so this is the object, and where is the image? You see the two light ray is parallel. So that means the image will form at a very far away place lah. Okay, so that means if your eye is here, what you will see is the light ray looks like come from very far away place. Okay, it looks like the light come from very far away. Okay, look like the light come from very far away because parallel. So that means the image will form at infinity. Okay, so image, oops. Image at infinity. Okay, image at very far, somewhere very far away. Okay, so characteristic of the image. So because if the image is at very far away, that means must be very big lah. You see the light come from very high up. So that means the head of the image is very high up at a very high position. Okay? So it must be big lah, so magnify. Next, this is upright. Because the light comes from the head right now, and the head looks like at the top. So must be upright lah. Head at the top, tail at the bottom, so upright. This is the image look like at infinity, but at the infinity there actually got light or not? No light. So this is virtual. Okay, this one, the position. So the image distance is at infinity. So image at infinity. Okay, like that. Okay, next we want to look at concave lens. Concave lens. Okay, we first look at the rules in drawing the ray diagram for concave lens. Okay, so the first one is the same as the convex. Ray which pass through the optical center travel in straight line through the optical center without being reflected. Okay, the first one pass through the center. Second one, the ray which is parallel to the principal axis is reflected and appear to come from focal point. Okay, that means light that parallel in will look like it come from focal point. And then the light that light will travel towards the focal point. That means if the light aim at the focal point over here, then it will refract parallel to the principal axis. So basically this number 3 and number 2 is opposite of each other lah. So it's the same, almost the same between the convex and concave. Okay, it's just that one is converge, one is diverge the light. Okay. Alright, so let's look at the ray diagram. Okay, concave lens. So draw the position of the lens. Oops. Straight line. Okay. Oops, sorry, got mistake. This one it should be like this. Oops, red color. Like this to show that it is concave. Okay, this is a concave. Okay, so this is concave lens. This is F, this is 2F. This is F, this is 2F. Okay? Alright, so now where is the object? Okay, the object is at 20 centimeters. So that means here. It is here. Now, light ray. The first one, okay, number 1, pass through optical center. Pass through optical center, you will pass straight through. Okay? One arrow before, one arrow after. Okay, next. Parallel going in. Okay, if parallel come in, parallel to principal axis come in, then it will refract away, look like from the focal point. That means like this. Okay, it will refract away, look like come from focal point. Okay, so that means the light like this. And we use dotted line. Dot. Okay, we use dotted line. So this is before, this is after pass through the lens. Okay, so where is the image? Where is the image? You see, the light come from here, go to here. Light come from here, go to here. So that means if you put your eye, if this is your eye, it will look like the light. Okay, it will look like the light come from here. Look like the light come from here. So this is the image. Okay, this is the position of the image. Object, image. Okay, like that. So fill in the table. Add 2F. So this is 20.0 centimeter. So okay, the image distance is just now is like 7 centimeter. Okay, 7.0. Image position is less than F. Okay, real or virtual? This is virtual. Okay, upright, inverted, upright. Size of image is smaller than object. Okay. Oh, I forgot to. Okay, characteristic of image. Diminish in size. Upright. Virtual. Because actually there is no light over here. The light does not actually converge here. That means you put a screen here, you cannot see anything. Virtual image. And then the position is less than 4. At 7 centimeter. Between F and optical center. Okay, between focal point F and optical center O. Now we don't label O here because O we already use for object, so we don't label O for the optical center. Okay, what happens for the image form for concave lens if the object distance becomes 15 centimeter? Okay, concave lens F to F, F to F. Okay, 15, that means over here. Alright. Now the light. First one, pass through optical center. Okay, one arrow before, one arrow after. The second one, parallel in, and refract, bend away, okay, diverge, okay, diverge. So one arrow before, one arrow after. So it look like okay, there is actually no light here. Okay, so the light coming in parallel and it will refract, it will diverge, okay, diverge. So now what does it looks like? Where is the image? Okay, where is the image? So if your eye is here, so it will look like the light come from over here. So this is the position of the image. This is where the image is. Object, image. Okay? So, characteristic of image. Diminish in size. Upright. Virtual. This is 6 centimeter between F and, that means between focal point and optical center. Okay, and then the last one, this one, what happens if it's at 10 centimeter? Okay, position of lens. Concave lens. This is F to F, F to F. Okay, and okay, the object 10 centimeter. So that means the object is at the focal point. Okay, object at focal point. Light ray, number one, pass through the center. Number two, parallel in, and then refract or okay, diverge. Okay, so before, after, before, after. So this is the actually there's no light here lah. Okay, that's why we draw dotted line. Okay, so where is the image? If your eye is here, look like the light come from here. Okay. Okay, look like the light come from here. Okay. So this is object, this is image. Characteristic. Characteristic of the image. Diminish in size. Upright. Virtual image. And the image distance is 5 centimeter between F and optical center. Okay? Between F and optical center. Alright. Okay, so let's fill up the table. Okay, so this is 15, this is 10, this is 6, 5, this is all the same, less than focal length, less than focal length. Virtual, virtual, upright, upright, smaller than object, smaller than object. So from here we can see that, what is it that we can see? For concave lens, don't care where is the object. Don't care where is the object. The image position will always be the same. The type of image always same. It's all virtual. The orientation of the image all the same, always upright. Size of image always smaller than object. Okay, so all the same for concave. Okay, you see or not? Okay, it's always the same. Don't care where the position of the object is. Okay. So discussion. State the position of convex lens with form real image and position of convex lens with form real image and virtual. So number 1. Real image when object distance more than focal length, and virtual image when object distance less than focal length. Okay. What are the common characteristics for real image formed by convex lens? Okay, common characteristic for real image is all real image are inverted. Okay, all real image are inverted. And opposite side. Opposite side of object from the lens. Alright. What are the characteristics of image formed by concave lens? I think only now. Okay, all the characteristics the same. So which is diminished in size. All of them are upright. All of them are virtual image. That is the characteristic of image formed by concave lens. Okay. Now, linear magnification. Okay, what is linear magnification? Linear magnification is the ratio of image height to object height. So, if you want to calculate the magnification magnification of the lens for different object distance. Okay, as you can see from the convex lens and concave lens also, when the object is placed at different location, different position. Okay, that means when the object distance is different, the size of the image will be different. Okay, so the way that we calculate linear magnification is we take the image height divided by the object height. So basically, it's a ratio the ratio between the image height to object height. So we can see from here that if the number for linear magnification is equal to 1, that means same size. Okay, that means the image and the object is the same size. If the magnification is less than 1, then that means the image is bigger. Okay, if the magnification is smaller, okay, the image is smaller than the object. If the number for the magnification is more than 1, then that means the image is bigger than the object. Okay? Alright. So ratio of image height to object height equals to ratio of image distance to object distance. Okay, this is what we will find out. Okay, this is what we find out between the image height, the ratio between the image height to object height and ratio of image distance to object distance. We find that they are the same. Okay? So that means that if we want to calculate the image height or the size of the image, we can use the image distance and object distance. Okay? To calculate the magnification, and then we have the magnification, we can get the image height from the object height. Okay, so basically we can write like this. We can we don't have to calculate the linear magnification at all. We can just relate these two together. Relate the image, the size of the object and image with the object distance, image distance, and the object height, image height. Okay, we can calculate Okay. Okay, let's look at exercise. Okay, figure 6.35 show an image seen through a convex lens with focal length of 10 cm. What are the characteristics of the image? Okay. Okay, so what is the characteristic? So from here we can see that is magnified. Okay, we can see that it's magnified. We can see that it's upright. Because the number, we look at the number, so we can know that it's upright. It's not inverted. And we can see that it is virtual, okay, virtual image. Why we know that it's virtual image? Because all of the real image, they are inverted. Okay, all real image are inverted. Okay, we can look at the ray diagram that we draw. Real image inverted. Real image inverted. Real image inverted. Virtual upright. Real inverted. Virtual upright. Virtual upright. Virtual upright. Virtual upright. So that means all image that is virtual is upright. So if you see that is upright, that means virtual. Okay? If you see the image is inverted, that means is real. Okay? But of course, this is only for lens. This is only for lens. Later on, when we look at image formed by spherical mirror, then it will be the opposite. Later on, we will discuss that. Okay, but for lens only, all upright is virtual, all inverted is real. Okay, so we know that is virtual image. Position, okay, position, because it's virtual, so the position is image same side as object. Okay. Because it's virtual. Because all of the virtual image is the same side as the object, and all of the image that is real, it will be in the opposite side as the object. Okay, opposite side of the lens. Okay, number 2, draw a ray diagram to show how the image in the figure is formed. So this is actual the kind of question that can ask in SPM. They show you like this and then ask you to draw the ray diagram. Usually come out in essay question. Okay, usually come out in essay. Okay, so what we need to do is in SPM, of course, it's not going to give you the graph paper, so we draw on a piece of white paper. So we just draw the principal axis, and then we draw the position of the lens. Okay, so this is the convex lens. They say that is convex lens, right? Convex lens, yes. Okay, convex lens. Okay, and then we it doesn't. We say length of 10 centimeter lah, but when we draw, we don't have to actually like measure 10 centimeter lah. As long as it is to ratio, then is enough already. Okay, roughly lah. Okay, I draw roughly. Okay, so now, how is it that we can get the magnified upright virtual image? The object must be, okay, the object must be less than, in between the focal point and the optical center. Okay, it must be like this. So I draw here lah. Roughly lah, okay, you can draw anywhere you like lah, okay, anywhere also can. Now draw the ray, okay. So the first one pass through the optical center. Second one parallel in, pass through focal. So if pass through focal like that, so that means the light will look like come from okay, I should draw down a bit. Okay, so that means look like the light come from here. Must label the direction of the light. Okay, looks like the light come from here. So this is the position of the image. Okay, this is the position of the image. So we draw dotted line. Okay, so this is the object, this is the image. So this is the ray diagram complete. This is convex lens. Okay, so when you draw ray diagram, make sure you draw like this. You must draw, you must position the object correctly. You must draw the direction of the light ray, and the light ray must go to the correct places. That means pass through optical center, pass straight through. Parallel go in, pass through focal point, and then you must be able to find out the correct position of the image, okay, and correct label for everything. So this is so usually in question like this, it's 3 or 4 marks, okay, for you to draw 3 or 4 marks. Alright, so the third one, so suggest a suitable position to place the object to produce an inverted image. So position the object more than, okay, at distance more than 10 centimeter from the lens. That means the object must be further away from the focal point, then we can get a real image. Okay? Okay, because this is convex lens. And any object that is further away from the focal length, then we will be able to get a real image with an inverted image. Okay, so